Welcome everybody to the Saturday, let's see, May 22nd general meeting, the Astronomical Society of Kansas City. Glad you all could make it here. Welcome. Okay, so Jackie, I'm going to turn it over to you and allow you to introduce or ask you to introduce our guest speaker, and I'm going to disappear.
And here I am. Good evening, everybody. Tonight we have with us Sarah Elizabeth McCandless. She works for the Jet Propulsion Laboratory as a navigation engineer, performing operational as well as pre-launch orbit determination analysis. Whoa. And has worked on a variety of flight projects, including MAVEN, InSight, Mars 2020, Europa Clipper, and Lunar Trailblazer. She also develops lots of multi-mission software tools and all sorts of things here. She earned a BS in aerospace engineering, guess where? At KU. Yay. Subsequently, she earned an MS in aerospace engineering from the University of Texas. And outside of work, she even actually flies Cessna 172s. Anyway, so we're really glad to have her with us here tonight. And actually, she's really with us tonight. She is speaking from Fairway, Kansas tonight. But her presentation will be an overview and status update on the most recent mission to Mars, the Perseverance rover, as well as discussing her role on her project and her journey to JPL. So everybody, here is Sarah Elizabeth.
All right, welcome everyone. It's nice to meet you all, even if this is just virtually. I'm excited to be here with you. Unfortunately, we can't be together in person, but I'm glad that we have an opportunity to meet tonight and talk about Mars and the Perseverance rover and lots of exciting things. So I'm going to grab the screen here and let's share again. Okay, so let me make this larger. Okay, so I think everyone should be seeing a full screen picture of the Mars rover. Hopefully that's the case. So my talk tonight is called Exploring Mars with Perseverance and Ingenuity. And I think everyone knows what Perseverance and Ingenuity are. Perseverance, of course, is our most recent rover that NASA has sent to Mars that landed back on February 18th, 2021. And Ingenuity is a helicopter that we sent with Perseverance. And that helicopter, if my mouse will cooperate here, is right here on the left of the main rover. So this is a selfie that the rover took sometime earlier this year, and is fun that we get to share that with you now. So I'll go ahead and dive right in here. So Perseverance, of course, is not the first mission that we have sent to Mars. I know I'm talking to an astronomical society, and so you may see a lot of things that are familiar to you, but just to sort of set the stage and make sure that everyone is on the same page, I'll just walk through some background information before I get into the nitty-gritty details of this mission itself. So we've sent a lot of missions to Mars over the past several decades. I have a number of missions here beginning in 2001, but of course we have missions that we sent to Mars even before that. We sent the Viking landers to Mars in the 70s. We sent other orbiters to Mars back in the 60s and the 70s. So 2001 was not the first time we sent something to Mars. But beginning sort of in the late 90s, early 2000s, we started this architecture of what we call follow the water. And so the missions that we sent to Mars to look for evidence of water and evidence of what we call habitability on the red planet. And so every time we sent a mission to Mars, we were trying to build on what we already knew and build on those discoveries, past discoveries that we had previously made, to try to answer the question of whether or not Mars was a habitable planet sometime in its past. And so you see that we have assets that we sent to orbit the red planet, all these orbiters up here, Mars Odyssey, Mars Express, the Mars Reconnaissance Orbiter, MRO in 2005, MAVEN, which is a mission I've actually worked on, and in 2016, ExoMars. And so this is actually a joint mission with ESA, the TGO Trace Gas Orbiter. And then we have just starting in 2003 listed here, but again, we sent things to Mars before that. but the Mars Exploration Rovers, Spirit and Opportunity, Phoenix in 2007, Curiosity in 2011, Insight in 2018, another mission I've had the chance to work on. This chart is a little bit out of date. This ExoMars rover that you see here was a planned mission to Mars by the European Space Agency that was delayed for a couple of reasons. So they're planning to go in 2022, I believe. And then of course, our rover that landed in 2021, just a couple months ago. And of course, now there's a new rover that landed just a couple weeks ago from China. So that is now on Mars as well. So we've sent a number of things that we are trying to use to learn more about the red planet, look for evidence of water, look for evidence of chemical components, and try to figure out really if life could have ever survived on another planet in our solar system.
Excuse me, Sarah Elizabeth.
Yes.
Could you go full screen on your presentation? We're seeing everything, but
oh, did I? Okay, I must have shared the wrong one. Thank you. Is that better?
Sure. Much better. Thank you.
Okay, great. Thank you. Okay. Oh, and I'm okay. Oh, now maybe my video is going to. Okay, great. So now let's make sure. Okay, great. Thank you. Okay, sorry about that, everyone. So now you can hopefully see the correct full screen here. So with all of those missions that we've sent to Mars in the past, we now know that there's lots of evidence that water did indeed flow on the surface of Mars. So both of the images that you see on the screen right here are artists' representations. Neither of these are real images. The present image, of course, is very similar to real images that we do have of Mars. And so today we know that Mars is dry, we know that it's dusty, we know that it's cold, we know that it has a really thin atmosphere. So we don't think that that's an environment conducive to supporting life. We don't expect there to be life on Mars right now. But there could have been life on Mars in the past, because we think that in the past, Mars looked like something that you see here on the left. So that we know in the past, there was a much thicker atmosphere at Mars. And so with a much thicker atmosphere, that means that the surface of Mars was a lot warmer. And so with a warmer surface, you could have liquid water. So we know that the planet was wet. We know that it was habitable. It had the right range of temperatures to support life. We know that the right building blocks existed on the surface of Mars. And so we have all of these components and all of the right pieces for life to exist on Mars, but we don't actually know if it ever was there or not. We've never discovered conclusively evidence of life at Mars. And so that's why we're sending this Perseverance rover. So we now want to answer the question, now that we know life could have existed, the environment was right, the chemicals were there, the water was there, that everything, all the conditions were right to support life. Now we want to try and figure out, did Mars actually ever have life? And so Mars 2020, or Perseverance, I'll use those two terms interchangeably, but I mean the same thing, is that next natural step in Martian exploration. And so there are 4 key science objectives for this mission that you see here on the screen. So the first is to explore a new landing site. The second is to actually seek those signs of ancient life. The third is to collect rock and soil samples that could potentially be returned to Earth, which is really exciting. And then the fourth is to pave the way for human explorations. So that's a pretty tall order for a single spacecraft, but hopefully Perseverance will be up to the job. So this is where Perseverance has landed on Mars. This is an image of Jezero Crater, and Jezero Crater was selected as the landing site for Perseverance by a group of scientists made up of individuals from around the world. And it actually took them years and lots of debates and discussion. I'm sure that all of the folks here are familiar with scientists getting together to try to make a decision. And so after a number of years, they selected Jezero Crater for a number of reasons. And I said that this is an image of Jezero Crater. It is. Of course, you know, Mars isn't yellow and green and purple. This image is colored by elevation. So we actually, you know, saw when you were looking at potential property for the Astronomical Society, you're looking at a topographical map, and this is a similar type of thing. So the brighter colors here, the yellow, is higher elevation. So those are cliffs and highlands, that kind of thing. And then as the color gets darker, the elevation is dropping. So this giant purple crater is the actual Jezero crater. And we think in the past that it was the home of an ancient lake. So this whole crater was filled with water. And if you have good eyes, you'll also notice that on the left side of the crater, kind of carving through these highlands, is what looks like a riverbed. So you can see it sort of snaking through and then emptying out into the west side of this crater. So not only are we choosing to go to Jezero Crater, we're choosing very specifically to go to the west side of Jezero Crater to sort of this delta area where this river is emptying into the lake. And the reason we wanted to go to that part of the crater is because we think, and by we, the mission, the scientists, everyone involved in the project, we think that there's this really high potential to find, potentially evidence of life, because there's going to be a lot of interaction of different materials from different parts of the planet that the river has brought, well, at the time, would have brought from the highlands down into this lake bed down here. So by going to this particular part of the crater, not only do you get the ability to study the crater and what the crater looks like here, but you also are able to study whatever the river dumped over here. So you sort of get a 2-for-1 in terms of geological exploration opportunities. And we have access in this particular area to rocks that are 3.6 billion years old. So that's really far in the past and relatively close in terms of geological time to the beginning of Mars. And so, that would have been when Mars was in that wetter, potentially more habitable environment. So it ups our chances of finding that evidence of life. And just for context, where is Jezero Crater on Mars? It is just north of the equator, right here. This is the Perseverance landing location. And then where is Perseverance in relation to other assets that we have sent to Mars? Well, you can see all of these other dots right here. Pretty much everything is near the equator of Mars, with the exception of Phoenix, which is near the North Pole. And I get the question a lot, oh, well, do the rovers ever, drive around and meet each other on Mars, or, go to the landers? And unfortunately, they don't. I think that'd be really cool if they did. We're not quite like The Martian, the movie, if anyone saw that with Matt Damon. So none of our assets have ever met up with each other on Mars, just because they're pretty spread out here, as you can see from the map. So that was sort of the first science objective. And now the second one is to look for evidence of biosignatures. And I think this is one of the things that's most exciting about Perseverance, one of the things that we haven't been able to do before. So for those who maybe aren't familiar with the term, a biosignature is something that only exists because a life-based process created it. So it could be an object, it could be a substance, it could be a pattern. Obviously, a really basic, simple example is a fossil. A dinosaur print only exists in rock today because a live animal was walking around millions of years ago to create that footprint. Now, we're not looking for things like that. It's more likely that we'll, see certain kinds of isotopes that maybe only exist because life existed in the past on Mars to create that kind of isotope. So that's sort of what we're looking for when we're talking about biosignatures. And there are 6 types of biosignatures that scientists are looking for. And so we need to find multiple independent fingerprints, biosignatures, to really be able to conclusively say that, yes, we found evidence of life. And this is a video. There's not really much sound, but hopefully the video itself is coming through and it's not too choppy. Oh, I guess there's a little bit of sound. But the other really cool thing about Perseverance is that we're going to be collecting Martian samples for the first time. So underneath the rover, in the belly of the rover, there's what we call the sample caching system. And so that has all of the sample tubes and the ability to store the samples. And we have a drill at the end of our robotic arm that we use to actually collect those samples. So in the video here, you can see the arm extending and then lowering the drill down to the surface. And then we collect a core sample, and then that's what we'll store in the belly of the rover. And when we've collected all of the samples that we can, we'll actually release that cache of samples on the surface and drive off. So Perseverance will leave the samples on the surface, continue to do science, and then a future mission will hopefully be able to return those samples to the Earth so that scientists here on our own planet will be able to study them. And a couple of people have asked me in the past, well, if we're sending this fabulous scientific instrument to Mars, why do we need to bother to bring samples back? And it's a fair question, because we do invest a lot of time, a lot of effort, a lot of energy to make sure we pack as much science as we can into the rovers when we send them to Mars. But if we're trying to look for evidence of life and effectively, change the course of history and say, look, we're officially not alone in the universe anymore, we want to be really sure. We want to have as many eyes involved in this project as we possibly can. And so if we can bring samples back to the Earth, we can use the full breadth and expertise of scientists around the world. We can use the full breadth and expertise of all of the laboratories with all of the instruments that we have that we just can't send to Mars. So that's why we're interested in bringing these samples back. And then the the fourth sort of goal that I talked about at the beginning was to pave the way for human exploration of Mars. Now, I know all of you know we've never sent humans to Mars, but of course, humans and robots need very different things to survive on the red planet. One thing, of course, is oxygen. Humans have to be able to breathe. Now, the atmosphere at Mars is 96% carbon dioxide. And as we all know, humans can't breathe carbon dioxide. We have to have oxygen. And so one of the instruments that we've sent to Mars with Perseverance is an instrument called MOXIE. And MOXIE is really cool because it will convert carbon dioxide in the Martian atmosphere into breathable oxygen. And it does that using a process called electrolysis that some of you may be familiar with. And so that oxygen hopefully will be breathable for humans, but then we could also use that oxygen for rocket propellant to potentially power vehicles to then return astronauts or samples back to the Earth. So I've sort of wrapped up now kind of the initial, science goals and objectives for the Perseverance rover. And so the next natural question, of course, well, okay, all that science is great, but how are we going to accomplish that? What is Perseverance going to be actually doing on a day-to-day basis to try to achieve all of those goals? And so this next little section is going to talk about all of the instruments that we sent with Perseverance. So for those of you who are familiar with Martian exploration, you'll notice that the Perseverance rover looks very familiar. So you see a artist's drawing of Perseverance on the left, or excuse me, on the right, Mars 2020, which looks very similar to the rover that we sent to Mars in 2011 called Curiosity. It's also known as the Mars Science Laboratory, or MSL. So the rovers look very similar, but they're actually pretty different. We've updated a lot of the science instruments. We've given Perseverance a number of cool new tools to make sure that it can achieve all of those objectives that we just talked about. So one of the big things that we changed with Perseverance were the wheels. The wheels are larger. They have a bigger diameter. They're thicker, and they also have more treads. So you'll notice that the Curiosity wheels on the left have a chevron pattern, and the wheels for Perseverance have dropped that. They're effectively horizontal lines. And so we've been able to actually double the number of treads that we have on the Perseverance wheels. And this is really important because it allows the rover to have better durability as it drives around on the surface of Mars, and to potentially drive over softer terrain, since we'll have a better ability to grip the soil or the regolith as we drive around on the surface of Mars. We've also packed Perseverance with cameras. So we have 23 cameras that sort of fall into 3 different bins. We have engineering cameras, science cameras, and then entry, descent, and landing cameras, and I'll probably refer to it later in the presentation as EDL. So EDL means entry, descent, and landing, which is the process by which the rover goes from the top of the Martian atmosphere and then lands safely on the surface. So just really briefly on this chart here, the engineering cameras, we have these hazard cameras here in the front and in the back. And these are cameras that we use to detect rocks, potential obstacles on the terrain, so that the rover doesn't drive itself into situations that it wouldn't be able to extricate itself from. We have a number of science cameras. So we have, in addition to the drill at the end of the robotic arm that I talked about a couple charts ago, we have 2 sides of the robotic arm. Oops, sorry, I think I have a Zoom pop up here. Let me minimize that. Okay, I don't need that. Okay, hopefully everyone can still hear me. So we have these 2 science cameras here at the end of the robotic arm, and then we have additional science cameras in the head of the rover. So when I'm talking about the head of the rover, you sort of, a lot of us think of this as the main body of the rover. Then we have a mast that goes up right here. And then we have this head on the top of the mast at the rover. And so in the head of the rover, we have a number of instruments that I'll talk about in just a second, but those also have a lot of cameras as well. So some of the cameras that we sent were specifically for that entry, descent, and landing EDL process. So hopefully a lot of you were able to watch EDL as it happened on February 18th. Obviously I did, I was there, but it was a really incredible experience. And then I think even just the next day, we started to get some images back. But for the very first time, we were able to see what it looks like to land on Mars. So this is a real photograph of the rover landing on Mars this year. And even though I've seen this photograph hundreds of times now, it still blows my mind away every single time. Like, this is real. This is what it actually looks like. This isn't an engineering simulation. This isn't an artist's drawing. This is real. This is what it actually looked like February 18th. So I won't go into the full details of EDL unless there are questions about it. But at the very end of that process, we had what we call a descent stage that lowered the rover on cables down to the surface of Mars so that it could touch down very gently and protect all of these really valuable science instruments that we sent to the red planet. And so this image was taken by a camera that was on that descent stage. So you can see the cables right here. So there's the cable here and then 3 cables here. And so these cables are lowering the rover to the ground. And then you can see Mars obviously here below. And then you can see the dust and the debris that's being blown around as the rover is being lowered to the surface. So now we'll get into the details of some of the scientific instruments, just because I know you're a more technical audience than the second graders I talked to earlier this week. But I talked about, cameras that are all over the rover. And these are 2 science instruments here in the head of the rover that involve cameras that we use to study rocks both near to the rover and far away. So this first instrument is called SuperCam, and we kind of think of that as an eye of the rover, if you will. That's this big opening right here. And so SuperCam fires a laser to study rocks that are up to 20 feet away from the rover. And so there's a spectrometer in this instrument, and that spectrometer is what we use to study the contents of the rocks that are, up to 20 feet away, and then figure out what they're made of. Then the second instrument that we have in the head of the rover is something called Mastcam Z, and the Z stands for zoom. So these are 2 cameras here, and they're also, it says here, they form a pair of rover eyes, if you will. So these are 2 cameras that we use to take wider shots of the context of Mars, if you will, I guess. To take, sort of more panorama shots, take pictures to sort of put all of the science that we're doing physically at the rover's location into context for where it is on Mars and what it's near, on the red planet. So is it near, cliffs? Is it near the edge of a crater? Is it near some really interesting rocks? And so we can use these 2 cameras to take all of those pictures, and we can take pictures in different wavelengths. We can actually take 3D images, which is really cool. We can take video. So both of these instruments are similar to instruments that we sent with Curiosity back in 2011, but they've been upgraded and they're a lot more powerful this time around. And this is a schematic to sort of hopefully better illustrate what I was talking about with SuperCam. So again, SuperCam is that instrument that was sort of that single giant opening in the head of the rover at the top of the mast. And so we basically fire a laser at rocks up to 20 feet away. And then that laser basically hits the rock and sort of pulverizes, obliterates, whatever verb you want to use, the rock into tiny little pieces. And then we use the spectrometer to study that those pieces to figure out what the rock is made of. And so we can actually study targets that are smaller than a pencil point with SuperCam, which is, I think, really cool. And these are 2 of my favorite instruments. Again, as a non-scientist on the mission, I think it's okay for me to have a favorite scientific instrument. But these 2 instruments are called Sherlock and Pixel. And so these are the 2 science instruments that are at the end of the robotic arm, again, with that drill that I talked about that we'll use to collect the samples. And Sherlock and Pixel are the scientific instruments that are going to be looking for those biosignatures that we talked about. So if we do find evidence of life, most likely it will be because of the work that we're doing with these 2 instruments. So Sherlock uses a spectrometer and a laser and a camera to search for organics, the chemicals that we need to build and support life. And then those different instruments search for organics, and then they can also be used to figure out if rocks have been altered by watery environments and then help us look for signs of ancient microbial life. And then Pixel, we use to study and identify chemical elements at a really tiny scale. And so the combination of these two instruments is really powerful because it allows us to study and map areas that are really small and really fine detail. And it's as close as we'll be able to get until we can send an actual human geologist to be able to sending a geologist to Mars. We're also sending a radar system to Mars with Perseverance, and this is an instrument called Rimfax. And so this is an in situ radar instrument that we're using to search for and identify geological features under the surface at Mars. And so you can see sort of the schematic here, potentially, you know, the kind of stuff that we'll be able to find with that instrument. We're also sending a weather station to Mars with Perseverance, and that is the META weather station. And you can see some of the different sensors that are here on the mast. And so META will help us measure wind speed, wind direction, temperature, humidity, and perhaps most importantly, the amount and size of dust particles in the Martian atmosphere. And so this may seem like the least exciting scientific instrument in some way, but it's perhaps one of the most important. If we're going to be sending humans to Mars, we need to understand the weather so that we can adequately design spacesuits and shelters for them to survive on the surface. And in particular, we need to understand how dust moves around in the atmosphere so that we design appropriate breathing apparatuses for humans that we would send to Mars. And so while we have assets at Mars that are orbiting from above and can take pictures of Mars looking down, and we can identify weather patterns on a global scale, we need more granularity than that to really be able to help humans survive on Mars. So by sending another weather station down to the planet, we have one more data point that we can use to help ensure the successful survival of humans if and when, you know, they're able to go to the red planet. So this is a real sort of animation, if you will, of the robotic arm as it was doing its first bicep curl at JPL a couple of years ago. And so again, you know, we have the two science instruments and then a drill at the end of that robotic arm. And so that's all that you're seeing here. And then you can see all of the different engineers here. We can play it one more time. And then you can see all of the engineers gathered around the rover watching it, making sure that everything is going as expected. And of course, I don't have to remind this audience, but if we send this rover all the way to Mars, if something breaks, you know, there's no one there to fix it. And so it's really important that we adequately test everything here on the Earth as thoroughly as we can ahead of time to make sure that it will be successful when it gets to Mars. And of course, no presentation about Perseverance would be complete without mentioning the Ingenuity Helicopter. And so again, this is an artist's drawing of the helicopter. And you'll immediately notice that this doesn't look like a traditional helicopter like you and I might think of one. It really looks more like a drone, but it is still a helicopter. It has the counter-rotating blades up here. It has a body, and then it has these 4 legs. This whole thing is really small. It's only 19 inches tall, and it weighs about 4.5 pounds. So this is really what we refer to as a technology demonstration. And so the only objective for the Ingenuity helicopter was to fly successfully at Mars and demonstrate that powered, controlled aircraft flight on another planet was possible. And very fortunately, and for a lot of us, you know, it was really exciting, that has now been proven. Ingenuity has actually had 5 successful test flights on the surface of Mars that have increased in length and complexity as the mission has gone on. And I actually have a video of a flight later in the presentation. So the helicopter was mounted in the belly of the rover. The rover is upside down in this image. You can see the wheels here and then an engineer in the background. And so you can see that the 2 blades are folded up right here. And then the legs are on top of the blades in this photograph, but when the rover's right side up underneath. And this is a photograph that we took, well, by we, I mean the rover, of course, that the rover took of the helicopter as it was being deployed. So the helicopter in this configuration is still attached to the belly of the rover, but you can get a sense for how tall it is and what the configuration looks like as you see these 4 legs deployed, the main body, and then the 2 blades up here. And so this is an embedded video, so let's hope that everything works. Okay. Let me turn up the volume on my side. So this is a couple minute long video, and you'll be able to find it on YouTube later because I won't play the whole thing for you today. But this is a video from the fourth flight, I believe. Yes, fourth flight of the helicopter. And so the rover was recording this video, and I'll stop talking so we can hopefully hear the helicopter now. Okay, so I don't know if anyone was able to hear that. It's hard for me to hear it, and I'm right here next to my computer. So I really encourage everyone to look this up after the presentation tonight to hopefully be able to hear it for yourself. But it's really cool that we have not only this demonstration of flight at Mars for the very first time, but we have this incredible video where we can both see it and hear it to get a sense for what it's like to fly on another planet. Move along for right now. Now, all of this science is really incredible and it's amazing, but it wouldn't be possible if you didn't arrive at Mars in the first place. And so as a navigation engineer, I can't give a presentation about Perseverance without talking about the trajectory and without talking about how we get to Mars in the first place, since that's my job. I was on the team that was responsible for developing the trajectory and then successfully flying that trajectory and operating the spacecraft on its journey to Mars to make sure that we got where we intended to go. And of course, it wasn't just our team. There were hundreds of people who were involved in that whole process. So just to orient everyone really quickly, we have the sun here in the middle. The Earth is orbiting about the sun on this blue trajectory. Mars is orbiting the sun on this orange trajectory. And then the rover is flying from Earth to Mars along this white curve. So it launches, it orbits the Earth once, and then it basically does half of a Hohmann transfer for anyone who's familiar with orbital mechanics to get out here to Mars. Now you'll notice on this trajectory that there are 6 dots that are explicitly labeled, and they're called TCMs. So a TCM stands for Trajectory Correction Maneuver. And a trajectory correction maneuver is something that we perform if we think that the rover is drifting away from this planned trajectory to Mars too much. And if it's drifting too much and we think the rover will not arrive at its intended destination at Mars, we perform a maneuver to basically nudge the spacecraft back onto that intended path. And so we have 6 opportunities to do that. One shortly after launch, one sort of in the middle of cruise, one late in cruise, and then a handful right before we arrive at Mars. And you can think of that, as tweaking the trajectory when we're really close to make sure that we hit that landing site exactly where we want to. Now, this whole process takes about 7 months. It took about 7 months for Perseverance to fly from Earth to Mars, and it flew about 300 million miles. And even though that was my job to operate it and to fly it, from Earth to Mars for those 7 months over those 300 million miles, those are still big enough numbers that it's kind of hard to wrap your head around. So if we bring it back a little bit closer to home, it's the equivalent of traveling from New York to Perth, Australia, here on the southwest coast of Australia. And I didn't denote the TCMs on this path, but you would have those same 6 opportunities to correct your path from New York to Australia. And for those of you who are golf fans and maybe Tom Watson fans, since we're here in Kansas City today, it's basically like Tom Watson hitting a hole-in-one where he is in New York and then the hole is in Perth, Australia. So hopefully that gives a little bit of context for how hard it is to fly something through space to another planet. As we're flying to Mars, we communicate with our spacecraft using something called the Deep Space Network, or the DSN. And a number of you are probably familiar with this. It's an interplanetary communications network made up of antennas that are around the world. And so we have 3 sites that we use to communicate with our spacecraft so that regardless of where a spacecraft is in space, one side of the Earth will be facing that object. So they're roughly equidistant around the globe. And we have a site in Goldstone, California, Madrid, Spain, and Canberra, Australia. And so all of these photographs are actually taken of the Goldstone, California location. I was able to visit on a work trip a number of years ago now. And so we have a number of antennas of different sizes. The largest antenna is a 70-meter antenna, and that's this picture here on the far right. And for context, if you can't, obviously, because you see that there's this structure supporting the antenna, but if you could stand directly under the antenna and look straight up, all you would see is the antenna. It would fill your field of vision. That's how big this is. And it's roughly the size of the Magic Kingdom castle at Disneyland, for anyone who's ever been to Disneyland. So this is a massive piece of equipment. And this photograph on the bottom, to maybe help drive that point home, is what this looks like from about, oh gosh, probably 6 miles away, 10,000 feet in the air, taken from a Cessna 172. So it was a picture that I took on a flight coming back from Death Valley, actually. So it's just a massive antenna. And then really briefly, just since this is a little more technical crowd, some navigation basics, since again, that was my role on the project. It was our job to make sure that we arrived at the landing site that the scientists had selected. So not only are we trying to get to Mars, we're trying to get to Jezero Crater, and we're trying to get to that very specific landing ellipse on that western side of Jezero Crater. And so as we're flying to Mars, it's our job as a team to determine what the spacecraft's state is. And by state, I mean position and velocity. So where is the spacecraft in space and how fast is it moving? So we want to understand where it is and how it's been behaving in the past so that we can predict where it will go in the future. And then we also we not only want to predict where it will go in the future, but then we also want to understand how certain we are about that prediction. And so if our prediction is going, somewhere that's not Jezero Crater, that would be an opportunity for us to perform one of those maneuvers that I talked about. And so what you see here in this picture are a number of ellipses, and they're the bigger ones are sort of the red and orange colors, and then they get smaller and the colors get more toward the cooler end of the spectrum. So your green, blues, and purples. And the chart on the bottom, or the key on the bottom, sort of gives a little more context as to what these ellipses are. So you'll see here, this red ellipse, this biggest ellipse that you see here on the chart, has a label of 0125. So this was an ellipse that we created on January 25th. And so on January 25th, we had a set amount of information, and we used that information to predict where the spacecraft was going to go. And then we sort of assessed how certain we were about that estimate. And so we thought the spacecraft was going to be to sort of this red check mark right here in the middle. And then we assigned an uncertainty to that. And that's this big ellipse. So we thought the spacecraft would be going to the center of this ellipse, but really it could have been going anywhere inside this circle. And where we want the spacecraft to go is somewhere inside this green box that you see here. So we're already in the green box, but we're not very certain about that. So if the spacecraft is somewhere out here, we're not in the green box. And so that means that we may not hit our landing site on Mars. So as the colors move toward that cooler end of the spectrum, you can see, looking here at the key at the bottom, that we're getting closer to landing. So we continue to do our analyses all the way up until landing day. And as we get closer to landing, you'll see that our estimates of where we're going start to kind of walk up in this northerly direction. But how certain we are about those estimates changes. We become more certain of where we are. And so these ellipses become smaller. So that's exactly what you want to see. If you see movement in where you're going, that's okay, as long as you're more certain about where you're going. And so at the end of the day, we actually have a really small ellipse right up here. And so we're in the green box, which is what we want. We're very certain about where we are. And so we felt like we had done our job. We delivered the spacecraft safely to Mars. And in fact, that is exactly what happened. So now I'm getting close to the end of the presentation too. I know we'll want to make sure we have time for questions. But this is a great video, one of my favorites, about landing day in particular.
Propulsion, go. EDL phasing, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. it will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The backshell has separated. Skycam maneuver has started. About 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So hopefully you understand why that's one of my favorite videos. It gives me chills and makes me teary every time, and I've watched it a lot of times now. But I think it's a phenomenal video that better than other videos that I've seen of landing, sort of captured really what it was like to be there on landing day when we landed on another planet. Oops, you don't need to watch it again though. So here are some fun photos from landing day. As I said, whoops, it looks like I think something just popped up that you guys don't need. Hopefully you can still hear me again. So these are some photos from landing day. Fortunately, I was able to go into JPL on landing day. Of course, with the global pandemic, the way we flew, the way we operated this spacecraft was very different than usual, not how we had planned or intended to operate it at all. But the team really rose to the challenge and did a phenomenal job operating this spacecraft as safely as possible and as safely as we could, given the circumstances that we found ourselves in. So these are a handful of photos. I'm working apparently very intently. It looks like here in the top right, everyone is celebrating at the moment of landing here on the bottom. This is some coworkers of mine and actually two of my bosses here on the lower left, and then a photograph in this main landing room after the celebrations had sort of died down. Let's make sure, there we go. So I also often get asked, how many people work on this mission? How big is the team? And hopefully this helps answer that question a little bit. So this was a photograph that was taken obviously pre-pandemic. There are no masks, no social distancing here. It was actually taken July 17th, 2019, a year before our first opportunity to launch to Mars was on July 17th in 2020. So this is a good chunk of the number of people who were working on the mission at that time, back in 2019. I will say that I think I was the only person from my team to go, and my team was 12 to 15 people. So hopefully that gives you a sense of, there are hundreds of people in this photograph, and this isn't even everyone who was involved. There were people who had worked on the mission and then, their roles had ended before this picture. There are scientists and other engineers who joined the project after this picture was taken. So it takes the combined effort and dedication and hard work of hundreds of people across, multiple years. For some people, more than a decade. I worked on the project for 6 years. So lots of efforts from combined individuals over a long period of time to make something like this possible. And it was just a privilege and an honor to get to be a part of, and something I'll always remember and always look back on very fondly. And normally I end the presentation here. Oh, I guess that's where I am in this picture. Normally I end the presentation here, but just because this is, hopefully maybe there's some younger members in the audience and maybe who are from this area, I'll just really briefly give a little bit about my background and how I ended up at JPL. So I'm from Kansas City, originally from Fairway. And I was really inspired by the pillars of creation. So for all the astronomers here, which I know is probably mostly everyone in the audience, it really was astronomy that got me on the path that I'm on now. And so prior to seeing this photograph, I thought space was just sort of, this giant black nothingness with just kind of pinpricks of light out there. And I didn't fully appreciate how much stuff was actually out there in the universe. And so I saw this image and realized, oh my gosh, there's dust, there's clouds, there's color. And so that was just really captivating for me. I think I saw this image when I was 5 or 6 years old. And it really entranced me and really sort of started me on this journey that I'm on now. And I went to the University of Kansas for college, where I got my degree in aerospace engineering. So rock chalk for any other Jayhawks in the audience. I was involved in a number of different organizations and activities when I was in college. I had a chance to study abroad for a semester in France, which was a really unique opportunity. And then I worked at Cessna as a flight test engineering intern after I graduated for 1 summer, and that was a fun experience as well. And then I went to the University of Texas at Austin for graduate school. And while I was in graduate school, I had the opportunity to work with data from a real space mission. And that mission is called GRACE, the Gravity Recovery and Climate Experiment. And so it's a pair of satellites that orbited the Earth, and they took gravitational measurements. And I used that information to create a drought index. And I can explain more about that in the questions if anyone is interested. But it was interesting for me because this was an earth science application, and obviously not at all related to what I'm doing as a navigation engineer now at JPL. So a lot of people, will ask, should I go to grad school? Should I not go to graduate school? When I'm in graduate school, I'm doing all this research. Does that mean I have to do that kind of research forever? And I always tell people, no, you don't, because I didn't. And so for those who are interested or young enough that that's still a potential path for you to go down, that's sort of how it worked out for me. And then from the University of Texas at Austin, I interned at the Jet Propulsion Laboratory 1 summer in between my 2 years of graduate school. I got a master's when I was down at UT. And then after I graduated, I went out to JPL and started working as a navigation engineer. So this is a fun photo. This is actually, I think, from my 2nd or 3rd day of work at JPL. I was on a mission called MAVEN. And if you remember all the way back at the beginning of the presentation, MAVEN is a spacecraft that's orbiting Mars and studying the upper atmosphere of Mars to really learn more details and try to figure out how the atmosphere has been stripped away over time. And so this is the navigation team. I was too new to the team to get a mission t-shirt. I'm not bitter about it. I still don't talk about it, 7 years later. And then from there, it's been great. I've had the opportunity to work on a number of really exciting missions. This is a photograph from landing day for the InSight mission, which landed the Monday after Thanksgiving in 2018. And this is a spacecraft on the surface of Mars that's studying the deep interior of the planet using seismology and a couple of other scientific methods as well that I can get into if there are questions. And then, of course, I've had the opportunity to work on Mars 2020, which has been phenomenal. And this is a photograph from launch. Of course, you can see the great mask here. And then I always include this just because I think it's fun. We had special badges for launch day that you can see here on the left. And then on the right, this is the reverse side of the badge. And it's a little hard for me to read the font. Oh, actually, I can look over here. Perseverance is not just a name, it's a way of life. So I thought that was sort of a nice kind of humorous nod to the circumstances we found ourselves in. We gave our rover a little face mask here. So it was sort of a nice nod to how the team was having to work and to support the mission over the past year. Someday I'd like to go to Mars as well. I'd love to be an astronaut. And we'll see, hopefully, that maybe can come to fruition. But even if, I go to another planet, there's no place like home. And especially for folks, from Kansas, hope you appreciate that image there. And then this is the last one. This is just sort of some other fun photos of my time at JPL. I've been able to work on a number of different missions. I haven't even talked about these non-Mars missions that I've had the opportunity to work on. So I'm happy to answer questions about those as well. But it's been a phenomenal experience. I've been at JPL for 7 years now, hope to be there for at least another 7. But I've loved, the people I've worked with, the missions I've been able to support. It's just an incredible environment. And with that, I will end my presentation. I'm happy to take your questions. And for those who maybe aren't already following or don't know where to get more information, you can check out all of these resources here. So our mission websites, and then of course, your favorite social media outlet, Twitter, Facebook, etc. So with that, I will happily answer any questions if there are any.
Okay, Sarah Elizabeth. Yeah, there's a couple of questions sneaking in here. First of all, thank you. This is an excellent presentation.
You're
Um,
welcome.
I was working at home, so my work computer was work. My play computer was watching the landing and everything I've seen since then. So,
Excellent.
okay, so a couple questions. Actually, they're starting to pour in here. So David McCallie's asked, in theory, could Perseverance find definitive evidence for life, or would that require returning the samples to Earth?
Yeah, that's a great question. Again, I'm not a scientist. I'm an engineer, and my role in the mission is actually over now. But as I understand it, the scientific instruments that we've sent, Sherlock and Pixel, have the capability to, I think, find enough independent biosignatures to say that we found life. I actually have, let's see if my backup charts are going to cooperate with me here. So hopefully this now is going to be a little bit clearer. So on the top, I believe this is a microbial mat that we've seen on the Earth. And so this is a breakdown of what that microbial mat on Earth looks like when viewed from the Sherlock and Pixel instruments. Now, again, my apologies. I don't know enough about the scientific details to fully explain what these different images are. But this is the kind of information that we're hoping to find at Mars. And so, based on these images, I would think and I would expect that they would be conclusive to be able to say that, yes, we found evidence of life. And then being able to return samples back, would help strengthen that story.
Okay, that's pretty cool stuff. Okay, Nancy Vaught is asking, what are the 6 biosignatures?
That is a great question. And off the top of my head, I don't remember all 6. Let me go back to that chart and see if I have some more information in my cheat sheet notes here. So I think, one is patterns in the rock. So fossil, kind of fossilized evidence. Isotopes are a second one. So isotopes are variations of a particular element. And so some isotopes can only exist because a life-based process did something to a particular chemical to change it in some way to create that new isotope. And so a type of isotope or a particular abundance of an isotope would be a second biosignature. And then chemicals and types of chemicals or abundance of chemicals is sort of a third fingerprint. But beyond that, I don't have more details. I'm sorry about that. Hopefully the internet or potentially, I would almost guarantee that our mission website has more information about that in particular and kind of what things the scientists will be looking for.
Okay, well, that's more than I knew. Thank you. Yeah, I've got several more questions here. John Bourne has asked, for Ingenuity, I think there were only 5 planned flights. I know there's at least a 6th planned now. As long as it keeps working, do you think it will continue to be used?
I sure hope so. As a technology demonstration, it's tough because the primary objective of the mission is not in any way related or tied to the helicopter. As a matter of fact, the helicopter had to be very explicit in its design that the operation of the helicopter would not impact the rover in any way. And so I would hope and I would expect that as long as the helicopter remains operational and that as long as operating the helicopter does not limit what the rover is able to do, that we would continue to use it as long as we can.
Okay, let's see. Another question from Terry Darrington said, can the twin mast cameras on Perseverance take stereoscopic images?
Yes, absolutely.
All right, let's see. Going down, Jim Stevens, who is in California, by the way. He says, I'm working on a project involving CubeSat navigation. Wonder briefly, as it's very specialized, if you use GMAT. We're working with it for our project and sounds like something you have all the time or some type of. Would take offline if you would have time.
Yeah, I think that would probably be something best discussed in more detail offline a little bit. but yeah, happy to talk about CubeSat navigation. I had some friends and colleagues who worked with CubeSats that we sent to Mars back in 2018 with the InSight lander. So I didn't work on those CubeSats. I was working on the InSight mission itself. So I know a little more of the details of that CubeSat navigation. I'm happy to talk about that in detail too.
Okay. We've got two questions, one from Terry Connor, another one from Alan Lehman. They're very similar, so I'm just going to smoosh them together, technical term. Says your job sounds very exciting and it's inspiring to see a Kansas graduate contributing directly to Mars exploration. So what are you working on next?
Yeah, it's a great question. So I'll just jump back to this slide just to make sure I don't forget any of the missions here. So I'm working on a mission called Europa Clipper. That's this mission logo right here. And Europa Clipper is really cool because Europa is a moon at Jupiter that has an icy crust, and then there's a liquid ocean underneath. And so scientists think that there is also high potential for life at Europa because any place on the Earth that we've ever found water, we have found life. Even in the really deep sea vents where there's incredible pressure, there's no light, near at the bottom of the ocean near these deep sea vents, even though there isn't light, there is still heat. So there still is a form of energy. You're obviously in water under the ocean. And then those deep sea vents are basically expelling and excreting chemicals into the ocean water. And so a type of life called extremophiles are actually able to thrive in that environment. And so scientists think that there may be something similar in that liquid ocean at Europa. And so we're very interested in sending a spacecraft to that moon to investigate and assess that possibility. And so before we can send something down to the surface of Europa, we're going to send a spacecraft to orbit Europa and learn more about the planet, help identify potential landing sites for a future Europa lander potentially. And so Europa Clipper is that mission. So I'm working on that. I've been working on that since 2019. It hopefully will be launching in the mid-2020s. And so that's really fun. I'm working on a mission called Lunar Trailblazer, and that's this mission logo right here. That's a mission going to the moon to learn more about lunar geology and lunar water and how that water flows around the moon and you know, kind of what the chemical components of that water are, which sounds kind of silly because we all know that water is H2O, but it's actually a little more nuanced than that. And so this mission Lunar Trailblazer is interesting. And then Dragonfly is a fun one. And I actually just started working on this Dragonfly mission a couple of weeks ago. So hopefully there aren't going to be too many detailed questions about that. But this is a mission to go to Titan, which is a moon of Saturn, and then land effectively kind of a flying rover, if you will, kind of a helicopter on Titan to do exploration of Titan. And so these are the three missions I'm working on now. And it's actually the first point in my JPL career that I'm not working on a Mars mission. These mission logos that you see here are all Mars missions, MAVEN, Mars 2020, of course, and then InSight. So it's a little bit interesting, you know, that I'm working on these kind of more outer planet missions with the exception of the moon right now. But it's always fun. It's challenging. It's nice to be going to a different body, a different place in the solar system. You know, leaving Earth and flying to Mars is not the same thing as flying to Jupiter or flying to Saturn. So it's an interesting challenge to be able to do something different and do something new.
Somehow, I think interesting challenge is probably the biggest understatement I've heard in a long time. Okay, more questions. William Gurley asked, were there any unsolved problems or was the mission perfect?
I wish I could say the mission was perfect. It was not. You know, we came up with a really detailed plan for how and I'll kind of specifically address this from a navigation perspective, since that was my role and is my experience and what I can speak to. So we came up with a really detailed plan for the mission, you know, that trajectory, that planned reference trajectory to get to Mars. We assessed a number of different contingency scenarios. You know, if this happens, how would we recover? Well, if that happens, how would we recover? And then on launch day, so literally as early as was physically possible to operate this rover, something happened that we didn't expect. And so, you know, the spacecraft went into what we call safe mode. So that's if an anomaly happens on the spacecraft, it basically goes into a mode to sort of protect itself and then sends a signal back to the Earth to say, hey, something happened. happened. I don't know what it is. So you need to figure it out and then fix me. And that happened, really shortly after launch, actually. And so it wasn't something that, was going to ever cause a loss of the mission, but it did mean that we were not able to talk to the spacecraft as early as we intended to. And so that made it harder, from the very beginning for us to know where the rover was. Well, I guess it was, still the full spacecraft at that time. So that was, is an example, that just from the very first launch day, there were things that happened that we weren't expecting. Later on in the mission, we actually had some solar weather that we weren't planning on. We can't even predict the weather here in Kansas. We can't predict the weather here on Earth. So of course we can't, accurately predict the weather in space. But we had some plasma that was actually impacting our ability to figure out where the spacecraft was. We never lost the spacecraft. I don't want to make it sound like that, but we need to know actually very, very accurately where the spacecraft is. And when we had all of that plasma streaming out from the sun, it basically, as it was flying past the Earth, started to interact with our ionosphere, the upper portion of our atmosphere. And so as the signals were coming back from the spacecraft to say, hi, here I am, those signals were getting jumbled. And so it just made it harder for us to really pin down where the spacecraft was. So that's another example of something that, wasn't in the plan, that we had to adapt to and sort of, figure out how to solve on the fly. And I think those are two of the big ones. And there were a couple of other things too. The spacecraft will always outgas. And so as any spacecraft that goes into space, when it reaches the vacuum of space, certain sides of the spacecraft will be hit by sunlight at different points in time. And when those sides of the spacecraft are hit by sunlight, that causes a chemical reaction that results in the spacecraft basically emitting gases off into space. And that can actually cause the spacecraft to move in a certain direction. You can think of it as kind of a really low power thrust, if you will. So, instead of an engine firing and, rapidly pushing you one way or another, just that light, releasing of gases can push you in one way or another. But that little amount of pushing in one direction can build up over time. And if you don't correct for that or model that correctly or know about it, it can cause you to miss the planet entirely. So that sort of happened. That was something that we expected to happen. So we were well prepared to handle that. But it's never perfect. I wish it was, but if it was, I probably wouldn't have a job. So.
Okay. Let's see. Joe Alberti is asking, will the helicopter be taking pictures?
Will the helicopter be taking pictures? Yes, I believe so. I haven't checked the mission website in a couple of days, so I'm not sure what new information, pictures of the helicopter or pictures from the helicopter, we have back. But I believe that's the plan.
Okay. Here's a question to put you on the spot. From Marty Rosenberg, he asks, as an engineer, do you feel NASA and the government or Musk and Bezos will take us further into space exploration?
That's a great question because I think it depends what you mean by further. So if you mean further physically, like distance wise, into physical space, I think that's going to be NASA and the government. Just the way, with the experience that NASA has, the Voyager spacecraft that we launched in 1977 are still operational, still traveling, and they've traveled so far that they're not even considered in our solar system anymore. They've passed into, what we call interstellar space. So that kind of experience and history and heritage that NASA has will continue to leverage and continue to build on, to continue to send things and do things that no one else has ever done before, to physically, go new places and to go, physically go farther. If you're talking, in terms of going farther as people going farther than they've done before, that maybe is a little more of an interesting question. Will NASA do it? Will SpaceX do it? Will a SpaceX NASA, joint effort do it? It'll be interesting to see what happens with the human landing system. A couple of weeks ago, maybe a month ago, time is sort of squishy here in the pandemic, but SpaceX was announced as the winner of the bid to build the human landing system for humans to return to the moon. And so that was a contract, that NASA put out and SpaceX won. So to return humans to the moon is going to be a joint NASA SpaceX effort. And a lot of, astronauts, the astronauts that we're launching to the ISS now, of course, are launching on SpaceX rockets. So in terms of getting humans to the moon, getting humans to Mars, it's likely that it's going to be some sort of joint effort. And whether it's SpaceX or someone else, that I don't know. SpaceX has a lot of experience. So it, a number of people would argue that it's or no. Ooh, sorry, let me move that back over here.
Yeah, I'm curious if Amazon will offer same day delivery,
Yes,
Okay.
maybe someday.
Okay, Bill Barlow is asking, says, thanks for the presentation. Says, will the weather data collected by the rover's weather station be available to be seen on a website like Curiosity was?
Yeah, that's a great question. And I fully expect it to be available. I was going to say, one of the sort of the benefits of a NASA mission, perhaps as compared to a private mission, is that as a government agency, everything we do is for the public, and we're funded by taxpayer dollars, and so it's our responsibility to share all of our data with the public. And so if it's not already up, I would expect that weather data to be available on a website. And I'm glad that the question referenced Curiosity, because I was going to say that other missions to Mars that have sent weather stations do have that data already available online for those who are interested in searching for it. So I would expect Perseverance to follow that trend. Absolutely.
Okay, sounds good. Let's see. David McCalley has another question. Excuse me. He said, did you explain what the Perseverance logo, the red and white, represents?
I did not explain, and I'm not sure that I have a great explanation other than the red, of course, is for the red planet. It looks cool, but I don't, unfortunately, that's a good question. I don't have a great explanation for the logo specifically, unfortunately.
I would have just guessed the red planet,
Yep, that's as far as I can guess as well.
Okay.
We did have, I'm trying to think, I don't think I have a photograph of the logo in here. But there's another logo for Mars 2020. So this is a logo that was created when the mission was approaching launch. And so this was the logo that we put on the rocket, on the launch vehicle, the logo that we have, for the mission shirt. I don't know if you can see that, but like on our mission shirts. And prior to this logo, we had a different logo that actually is really cool. It was 2020. And then there was Earth and Mars were the 0 digits in that 2020. And then there was an orbit sort of connecting those two zeros together. And so that was actually a really cool mission logo as well, because it sort of was referencing, from Earth to Mars, and then, collecting the samples at Mars and potentially returning those to the Earth. So that's a different mission logo that had a little more nuance and subtlety to it that was cool. But it was a little more complicated to paint on the launch vehicle. So we came up with a more streamlined logo, and that's pretty common for a lot of missions. You can see InSight's the same way.
Okay. David's got another question here. It's a navigation question. So he asks, how does the flying craft know exactly where it is during the flight? Does it solve for its position against the stars? And if so, how frequently does it have to solve it?
That is a great question. And I have a slide that talks about that. So I don't normally go into the details, but since you asked, hopefully I won't make you regret it. So on the Earth, when we're trying to figure out exactly where we are, we use GPS, Global Positioning System, to triangulate exactly where we are. Now for interplanetary navigation, of course, we can't do that. We're beyond the range of GPS satellites. And so we have to triangulate where we are in a different way. And so we use 3 measurement types to do that. And so the first 2 are what we call line of sight measurements. And so the first is a range measurement. And so hopefully, you can see me. I tend to talk with my hands a lot. So hopefully this will come through via the Zoom here. Excuse me. So first we want to know how far away the spacecraft is. So we have an antenna on the ground that will send a signal to the spacecraft, and then that signal is received by the spacecraft and immediately sent back to the Earth. And so we measure how long it takes the signal to go to the spacecraft and come back, and then we can convert that time into a distance measurement. And so you can kind of see that here. So, we send the signal up to the spacecraft and then the signal comes back. And so that allows us to figure out how far away the spacecraft is, and that's our range measurement. But then, of course, the spacecraft isn't staying in one place. It's flying to Mars. So not only do we need to know how far away the spacecraft is, we also want to know how fast the spacecraft is moving. And so that's what we call a Doppler measurement. And so I probably don't need to explain Doppler to astronomers, but in the context of navigation, we're interested in how that signal that we send to the spacecraft is changed by the spacecraft when it returns that signal. So we send the signal to the spacecraft, and then because the spacecraft is moving away from the Earth and from the ground antenna, the frequency of that signal changes when the spacecraft returns that signal to the Earth. And then we can interpret how much that signal has changed into a Doppler measurement to then figure out how fast the spacecraft is moving. So that's great. So with the range and the Doppler measurements, we now know kind of, hopefully with my hands here, you know, if my right hand is the ground antenna and my left hand is the spacecraft, we know how far apart the two objects are, and we know how fast the spacecraft here on my left hand is moving away from the ground. But that doesn't really tell us exactly where the spacecraft is on that plane. So again, if my spacecraft is the left plane of my hand, you know, I'll kind of pivot to the camera here and hopefully you can see this. The spacecraft could be in the center of my palm. It could be at the tip of my index finger. It could be at the tip of my pinky finger. So we need some additional measurement type to sort of narrow down where we are in the plane of sky. And so to figure that out, we use something called a delta door measurement. And so that stands for delta differential one-way range. And so this is an example from Curiosity, the Mars Science Laboratory. And what a delta door measurement is, we actually use quasars. And so I know you were talking about quasars in the introduction here. So we use those same ground antennas to point to the spacecraft and then point to a quasar and then point back to our spacecraft. And because quasars are so stable in terms of their brightness, we have a good idea of, you know, how far away that quasar is and what the angular measurement of that quasar is. And then we can compare that measurement to our spacecraft to get an angular measurement to then figure out if the spacecraft is on, you know, the palm of my hand versus the tip of my pinky finger. So combining all three of these measurement types really triangulates where we are in space. And in terms of the frequency of these measurements, that changes depending on where we are in the mission. So for a large portion of the mission, when we're just sort of in regular cruise, just kind of flying through space, doing our thing to get to Mars, we talk to the spacecraft about 8 hours a day using range and Doppler measurements. And we perform these plane of sky measurements only a couple times a week. And then as we get closer to Mars and closer to landing, all of that increases. So the final 45 days of the mission, so that was starting right around the new year because we landed on February 18th, we started implementing what we call continuous tracking. And so that means that we were continuously getting range and Doppler data back from the spacecraft. And then we started to get this delta door information. We went from twice a week to once a day to then twice a day as we were getting really close to landing. And this is getting a little more into the technical detail here, but as you get really close to Mars, it's actually really cool because the gravitational field of Mars starts to pull the spacecraft in, and it actually physically bends the trajectory as the spacecraft is coming into Mars. And so we know that happens. We've seen it happen before. In just basic physics, we understand that that's a phenomenon, but it's still hard to predict exactly how the trajectory will be bent. And so it's really important to get these plane of sky measurements in particular, because that helps us understand how much the trajectory is being bent to then understand if we need to perform one of those trajectory correction maneuvers that I talked about. So that was a lot of detail, but hopefully that helps answer your question of how we, really specifically perform navigation for a spacecraft flying to Mars.
Actually, it's fascinating stuff. The calculations, the being able to compensate for the angular displacement for the Doppler and all that sort of stuff. That's amazing stuff. I guess it really is rocket science.
Yes.
So. Okay, let's see. I think that's all the questions. Jay Manifold and Alan Lehman also shared a couple of websites on the chat window. So anybody who's watching, if you open up the chat, there's the websites where you can look for the weather data from Mars 2020 mission. And now all I'm seeing is everybody's going, wow, what a great presentation. And I must say, this has been fun. It's the next best thing to being there. I'm only slightly jealous.
Well, thank you. It's fun for me too. It's a good reminder that what we do is cool. You know, it's something, you know, when you live with it day to day, sometimes it can be like, well, yeah, of course, you know, it's just a job. But it is really fun. And it's also great too. I think it's really important for us, you know, at NASA, especially, you know, because again, you know, we're a government agency. I think it's really important to be able to share what we do with the public and get people excited about it and explain that, you know, we're not wasting your tax dollars. We're trying to pull as much as we can out of them and use them as best we can.
Well, of course, you've got kind of a biased audience here, but I don't think anybody's even remotely suggesting you're wasting the tax dollars.
I hope not.
Yeah, it's fascinating. I think considering what the incredibly small percentage of our budget, I think NASA gives us an incredible return on our investment. So
you won't get an argument from me.
So anyway, lots more thank yous from lots of folks. And one person, Mark Blanken in particular, says, look forward to an update from you for your current mission. So
Happy to come back anytime.
okay.
Maybe in person someday.
Yeah, we're all keeping our fingers crossed on that one. So, okay, well, I think that pretty much wraps up all the questions. So Sarah Elizabeth, thank you so much for taking your time. I mean, you know, I wish it was clear and we'd go out to Powell and look through the telescope, but the monsoons are upon us and our weather forecasts aren't nearly as good as Mars, so I think. So, okay, I guess I'm going to sign off now for everybody. So once again, thank you very much for doing the presentation and like I said, great adventures you're having. I'm only again slightly jealous. So.
Well, thank you very much. It was great to be here. I appreciate the opportunity.
Thanks,
Okay.
Sarah. I'll be in touch with you. Okay. This is Jackie.
Sounds great, Jackie. Thank you.
All right. Welcome everybody to the Saturday, let's see, May 22nd general meeting, the Astronomical Society of Kansas City. Glad you all could make it here. Welcome. We'll do our usual call to order welcome, which is pretty much what I just did. Okay, so our first update is our ASKC library update. And Alan, I'm going to ask you to unmute and start video if you want to give us an update.
All right, not too much to say this evening. Melinda remains unavailable for the time being. In the interim, I'll serve as librarian. I encourage you to continue to use our fairly expansive library. Just a reminder, we have somewhere just below 500 books in our library and other media. And there's a full catalog online at askc.libib.com, askc.libib.com. And you can use the patron login function there if you want to check out a book or put it on hold, or just send an email to myself at treasurer@askc.org. That's all I've got.
All right, thank you, Alan. Okay, so David, I had you here for a minute and I lost you. So if you want to give us an update for the Powell Observatory, David, start your video. Up there you are.
Yeah, you thought I was alive. Yeah, you all probably know by now that we've restarted our public nights. COVID has impacted many of our members and some have moved out of town. Our teams are a little short. So if anyone would like to volunteer to be on a team on our public nights, which are going to be the first and third Saturdays of each month, we could use some more staff members. You don't have to be a key holder, just someone willing to show up and assist the teams that are on duty. If you'd like to volunteer, please get in touch with me. Your emails or how to get a hold of me are on every issue of the Cosmic Messenger, or you can call the ASKC information line and you'll get me. It's 913-438-3825. Gerald and I went out to DeSoto and picked up a donated telescope, and we already have two 16-inch Dobsonians, so we're going to sell this one to raise money for the observatory. So if you're interested in a 16-inch Dob, once again, give me a call and we'll arrange for you to have a nice 16-inch telescope. The other thing we've been working on recently, about 10 years ago, the ASKC established a scholarship fund to give scholarships to UMKC students interested in astronomy. It's grown now from about $10,000 it started with, had an additional 1,500 or so donated since that time. The last donation was in 2016. You'll notice in the newsletter, there is a little form to add donations to it. We've recently resurrected it. There's now about $19,300 available in there to give out. We've only given out one scholarship in the past 10 years. We'd like to give out a few more. So if you know anyone that's a UMKC astronomy or physics student, have them get in touch. You can see how to get a hold of us on the newsletter every month. And that's all I have for the moment.
Okay, so I just got a message from Scott Kranz. He's our dark sky site director. Evidently, our dark sky site has been getting even more rain than we are. So obviously, nobody's going out because of the rain to observe. But if you do go down the dark sky site, the showers, I think, have been installed. The hot water heater and the showers are up. We had to get a new propane, refill the propane tank. Otherwise, you get cold showers. But if you do go down, please make sure that you stay on the gravel area, which is pretty much overgrown by grass, I think. But please walk the field before you pull your vehicle out, because otherwise there's a good chance you may get stuck. And it's a long way to get a tow truck from Butler. So please be careful out there. As shown on the previous slide, we're doing Powell Observatory on the first and third Saturdays of the month. Our second Saturday, we're still doing the Zoom programs, both on Zoom webinars and also via Facebook for our second Saturday astronomy. And unfortunately, I forgot what our program is for June 12th, but there will be a second Saturday astronomy program. There's more information on our website, and there will be postings on our Facebook page and in the Cosmic Messenger newsletter. The other thing I want to remind everybody about is that we are having the elections next month. So the Saturday, June 26th general meeting, you'll be able to, well, you should have your ballots cast by then. It's a little bit difficult to do in-person balloting, so you have two options. One would either be to mail in the ballot that you'll receive in the in the June Cosmic Messenger. Also in the Cosmic Messenger, there will be instructions on how to vote online. So you've got two means by which you can cast your vote for the officers. Let's see, but all votes must be submitted by the June 26th election to be valid and to be counted. Okay, David Levy just texted me, or some media form. So David, if you can hear me, I've just promoted you to a panelist. So if you want to speak up, there you are. So I'm going to, whoops, wrong one.
Well, thank you.
There you are, and start your video.
I even have a camera here, so I can start my video here. I have been commanded to do so. Okay. And I wanted to add my welcome to everybody. And tonight, actually, I was going to just put in the quote as a chat, but that quote was, "And it all began today." And that quote could deal with almost anything in astronomy. It was actually uttered by Jules Bergman, ABC News, on the launch of Telstar in the summer of 1962. But the quote that I want to really do is the one from Carl Sagan in 1980 about radio telescopes. And he said, "Modern radio telescopes are exquisitely sensitive. A distant quasar is so faint that its detected radiation amounts perhaps to a quadrillionth of a watt. The total amount of energy from outside the solar system ever received by all the radio telescopes on the planet Earth is less than the energy of a single snowflake striking the ground." I thought that was kind of neat. Anyway, thank you very much and enjoy your meeting. Back to you.
Okay. Thanks, David. It's always good to hear from you. I'm sorry we missed out on getting you included earlier, but always glad to have you. A couple of updates on the Powell Observatory relocation efforts. The fundraising committee made a presentation to the board to recommend hiring Keller and Associates fundraising consultants. They are out of Lawrence, Kansas, to actually conduct our fundraising efforts, which we anticipate starting sometime this summer. This will be the formal fundraising, so we're out to raise enough money to relocate and build a new observatory. Right now, they submitted a contract proposal. We are having that reviewed by legal staff. Once that goes through, we will sign the contract and we will start fundraising. So guess what? It's real. Okay. One other development that kind of took some of us by surprise, but it looks like it has a very, very promising potential is, I'm going to go to my next slide here. As everybody should know, we've been negotiating with Cedar Cove about relocating the observatory to a site on their property. They're very good people to work with. And on the slide that you should be able to see on your screen right now, the dashed red line is the Cedar Cove property. They have 142 acres. And the dashed blue line is where they propose to basically give us, well, not give, but at least to us like $10 a year for 99 years, 10 to 12 acre site. The area marked in black, the reason this all came about is we talked to the property owners about running utility easements through their property. The reason for that is because basically the utilities that exist along Highway K68, very limited water, and the electricity we'd have to run the electrical and the water roughly a half a mile through very rocky terrain. So we contacted the property owners immediately west in the black area about seeing if we could work in a utility easement with them. And they said, well, we've got 77 acres here. Would you be interested in buying it? So the construction committee went out, walked the property, and it was unanimous for many reasons. For one thing, the property is adjacent to Mission Bellevue Road, which is a paved road. This is very close to the Circle Grove school site that we also contemplated. The other thing, I don't know if you can read topo maps, but if you can see my mouse cursor, this is the area of the proposed observatory site. The new proposed observatory site would be roughly in this area. It is 80 to 85 feet higher in elevation. So basically at this side, you'd be looking uphill. These are all uphill gradients. This puts us at least 80 feet above that area. I've also met with the Cedar Cove folks. They are perfectly fine. They understand that, it's a better site location for us. We still anticipate doing a lot of joint ventures with them as far as outreach activities. And also, this is kind of a unique opportunity because between the two properties, we would have approximately 220 acres, and this would be a regional attraction. Basically, the Cedar Cove Big Cat Conservancy, and obviously the observatory and astronomy outreach. So we're in the preliminary stages of negotiating this and investigating. The property owners are definitely interested in selling. We have not settled on any kind of a price. Once that becomes real, of course, that's still going to have to be approved by the board and then presented to the membership. Okay. I'm sure there's lots of questions, but right now there's not a lot of answers. So if we could hold off on the questions regarding this, we'll do a dedicated update on this later with the membership. Okay, so now Jay hasn't thrown anything at me yet, but I've decided to call this his manifold minute. Whoops, if I can get the right one. Yeah, and even if it's more than a minute. So Jay, let's talk about the May supermoon eclipse.
This is going to be one of the bigger astronomical events. It is Wednesday morning. The umbral phase, which is the part where it starts really looking like something, is at 4:45 a.m. Central Daylight Time is when that begins. Now, the sunrise and moonset times that I have there are specific to Kansas City, so they will vary depending on where you are as well. To get a good general idea of the visibility of this thing, look in the kind of in the lower right, that map of the world, and find where you are, and it will indicate what portion of the eclipse is going to be visible to you here. But it's still going to be visually very striking, and this is where I mention go out to that website there, Photo Ephemeris, and you can use the photographer's ephemeris to line up photography and get pictures of the setting eclipsing moon behind interesting things like the city skyline or some sort of landform or just whatever you want. So that's a fun thing to do. And again, that is early next Wednesday morning.
Well, thanks again. Have a good night and stay safe.